Hey folks, Ms. Gosling here. In this video, you are going to learn about half-life, not the video game, the nuclear physics concept. And by the end of the video, you'll be able to solve half-life problems. So let's go ahead and get started. I'm going to start by defining half-life. And we say that half-life is the time it takes for half of a sample of an element to undergo nuclear decay. Now, there's a couple words that are missing here. So first of all, when we talk about half of a sample of an element, we're talking about an unstable element. The reason that we have to add the word unstable is because a stable element, so for example, the most common isotope of iron, is not going to go through nuclear decay because its nucleus is already stable, so it doesn't need to change to a more favorable nuclear configuration. Now, the other word that I want to add is the word large. So half-life is a statistical, is a probability. And I think a good analogy here is to think of a coin flip. So if I take a single coin with heads on one side and tails on the other, and I flip it once, I have a 50% chance of hitting heads and a 50% chance of flipping tails. If I take two coins and I flip them at the same time, yes, I have a 50% chance of hitting heads or tails with each coin, but that means that 50% of the time, I should have one head and one tail, and 25% of the time, I should have two heads or two tails. So you can see that half the time, half of our coins will quote unquote decay, but the other half of the time, either both will decay or neither will decay. So when we have a small sample of coins, our 50% probability is not necessarily as predictive. However, if I were to flip 1,000,000 coins, I would be much more likely to hit this 50%, or to get close to that 50% number. So I'm much more likely to have 50% of my coins flip a heads, for example. The same thing is true with a sample of unstable nuclei. If I have two unstable nuclei, the chance that both of them will decay within a half-life, or that neither will decay within one half-life, is equal to the chance that one will decay and one won't. But if I have a large sample, so for example, if I have 1 mole of something, or approximately 10 to the 23rd nuclei, it's much more likely that half of that sample will decay within my first half-life. So that half-life equation, or that half-life value becomes much more predictive the larger our sample is. So moving forward, I want to talk about how we measure half-life. One of the most common tools for measuring half-life is the Geiger Counter, pictured up here on the right. So a Geiger Counter is a tool, in this image, just so y'all are aware, just comes from an Amazon post of someone selling a Geiger Counter. So Geiger counters are a tool we use to measure radioactive activity, and they measure, and so what we want to do with a Geiger counter is we want to measure the background count rate per second. So we want to see how many, what kind, so our environment is, atoms in our environment are constantly undergoing radioactive decay. So we are constantly having those radioactive particles get released into the environment. So we have to know what's the background radiation in our area, because if the background rate is significant, that is going to affect our sample count rate. So what we're going to do is we're going to start by measuring the background count rate. So we're going to just kind of hold our Geiger counter up into our environment, and we'll see how many, what the radioactivity is. Then we'll put our Geiger counter in front of a sample of a radioactive material, so for example, uranium. And we're going to measure the count rate of our sample per second. So how much decay is happening per second with our sample. We will subtract 1, you can see I miswrote this here. We'll subtract 1 from 2 to figure out what the actual decay rate is, or what the actual activity is in our sample. So we need to make sure that we are not counting the background radiation in addition to the radiation from our radioactive material. So here's an example of a half-life problem. So thorium-227 has a half-life of 18 days. if its initial count rate is 50 counts per second, what will its count rate be after 36 days? So our givens for this problem are our half-life, or T1 half, which is equal to 18 days. And you can see I forgot to highlight that while I was reading. We also know that our initial amount of activity, which we're going to call A naught, is 50 counts per second. And we know that the time that has elapsed is 36 days. Our unknown for this problem is the count rate after 36 days, or A of 36. Once we have figured out our givens and our unknown, we're ready to talk through our equation. So we know that after one half-life, the activity in our sample will be 25 counts per second, because the activity should be split in half after one half-life. So we want to figure out how many half-lives happen in 36 days. So T over T1 half is equal to 36 over 18, or 2. So another way to word this problem is what will be the activity in our sample after 2 half-lives, since we're undergoing 2 half-lives. So we know that after one half-life, our activity is going to be 25 counts per second. After 2 half-lives, we'll divide this number in half again. So we need to have 50 divided by 2 for one half-life, which is 25. And then we'll say, okay, so we need 25 divided by 2 for our second half-life, which is going to be 12.5 counts per second. And that is the solution for our problem. And you can see here I kind of combined our equation and our sub and solve steps here, because we don't really have a good equation for whole half-lives. And the easiest way to figure out the activity or to solve half-life problems if we have a whole number of half-lives happening, so 2 half-lives or 3 half-lives, is to follow this method. Now we could also, of course, rewrite our equation. This is 50 over 2, which is equal to 50 over 2 times 2, or 50 over 2 squared. Another way that we could rewrite this, therefore, is that our activity after a certain amount of time is equal to our initial activity times 1 over 2 to the t over t1 half. So 1 over the number of half-lives that have elapsed. Or 1 over 2 to the number of half-lives that have elapsed. So with that, that'll bring us to our more general equation, where we ask what happens if our time isn't a multiple of the time for one half-life. So for example, if we were measuring this count after 38 days instead of after 36 days, what would we expect to see? And that brings us to our 2 nuclear decay equations. Now both of these equations are talking about the same thing, and the equation that you use is actually going to be dependent on what information you're given. So our first equation both equations give us the number of counts, or the activity, after a given amount of time t. And in both equations, we are multiplying our initial activity by a constant, or by an exponential of some kind. So in our first one, we are looking at our half-life. So if we are given our half-life, we're going to use our first equation. And in our first equation, what we're going to do is we are going to multiply our initial count by 1/2 to the t over t1 half. So over the time elapsed divided by the time for one half-life. And that will give us our activity after a given time. Or instead of, so right now we actually have the number of parent nuclei after our given time. We could also replace n of t with a of t and n naught with a naught to give us the activity. Either equation works, and it's really dependent on, again, what information you're given at the beginning. So that's our first equation. The only difference between our first equation and our second equation is in our second equation, instead of having our half-life, we have lambda, which is our decay constant. And if you're given your decay constant instead of your half-life, you'll know that you need to use this equation. There's a third equation that involves tau, which is our time constant. We're not going to worry about that one, but if you're given a time constant, we'll use the equation with tau. In class, we went over the relationship between t1/2 and lambda. And I want to go over that really quickly one more time. So setting our two equations equal to each other, we know that n of t is equal to n naught times 1/2 to the t over t1/2, which is equal to n naught times e to the negative lambda t. Canceling out our n naughts, and also changing the format of our exponent here, we can rewrite this as 2 to the negative t over t1/2 is equal to e to the negative lambda t. And all I'm doing here is I'm bringing my 2 to the numerator of my fraction by making my exponent a negative. And this is something you've seen before, right? So 1 over 2 to the 2 squared is equal to 2 to the negative 2. We're doing the same thing here, just with variables instead. Now, I don't like having my lambda and my t1/2 in exponents. So what I'm going to do is I'm going to take the natural log of each side in order to move them down. So here we go. So now that I have the natural log, what I can do is I can actually move my t over t1/2 and my lambda t to the front of my equation. So I can say negative t over t1/2 times the natural log of 2 is equal to negative lambda t times the natural log of e. Simplifying this further, the natural log of e is 1. So the right side of my equation will become just negative lambda t. So I get negative t over t1/2 times the natural log of 2 is equal to negative lambda t. Again, my negative signs will cancel, and my t's will cancel. And what I will get is that the natural log of 2 over my half-life is equal to lambda. So if you're given your decay constant and you want your half-life, you can easily get that. And if you're given your half-life and you want your decay constant, you can do the same. So I just want to make sure that I give you this relationship because you may need to use it in the future. Okay, so that brings us to a second equation. Thorium-227 has a half-life still of 18 days. If its initial count rate is 50 counts per second, what will its count rate be after 837 days? So again, my givens are just about the same as they were last time. I know that my half-life is 18 days, and I know that the time that has elapsed is 837 days. I also know that my initial count rate, so n naught, is equal to 50 counts per second. And that means that I am ready to identify that my unknown is my count rate after a time t. So my count rate at 837 days is some mysterious number. So knowing that I have my half-life here tells me that I have to use the half-life formula, the half-life version of our activity equation. So I'm going to say that n of 837, or not even putting in numbers. Yeah, we'll say n of t is equal to n naught times 1/2 to the t over t1/2, which means that I'm ready now to sub and solve. So I know that I want to find my count rate after 837 days. And so that tells me that what I want to write in here is that the n of 837 is equal to my n naught, which is 50, times 1/2 to the 837 over 18. When I plug that into the calculator, I get that my count rate after 837 days is 5.0 times 10 to the negative 13th counts per second. So at that point, my thorium-227 has basically completely decayed. So this is a similar question, but this time I want to use the decay constant to find its count rate after 837 days. So again, my givens are the same. And my unknown is still my count rate after 837 days. But this time, I want to find lambda before I find my unknown. So I have to use two equations here, right? So first, I'm going to need to use that the natural log of 2 over t1/2 is equal to lambda to find lambda. And then once I've used that, I'm going to use n of t is equal to n naught e to the negative lambda t to find n of t. So with no further ado, let's go ahead and get started. So when I sub and solve, what I'll get is that the natural log of 2 over my half-life, so the natural log of 2 over 18 is equal to lambda. So lambda is 0.038. Plugging that into my equation, I get that my count rate after 837 days is equal to 50 times e to the negative 0.038 times 837. And when I put that in a calculator, sure enough, I get the exact same answer I got last time, that n is equal to 5.0 times 10 to the negative 13th counts per second. So let's go ahead and talk takeaways. First of all, the half-life of an isotope is the time it takes. Half-life of an isotope is the time it takes for half of a sample of that isotope to decay. We can use the exponential nuclear decay equation to determine the amount of sample left over a given time, and the decay constant is another way to measure the stability of an isotope, and is equal to the natural log of 2 over our half-life. So with that, this is everything I just shared with you about half-life. I'm going to go ahead and give you guys a chance to try solving some half-life problems on your own. Best of luck, and happy solving.